All right, audience, settle down. We're starting. Okay. Yes? Okay, so welcome to part 2 on reinforcement learning, hidden theory, and new superfast algorithms. So as you recall, this was basically a long history. I mean, joint work starting back in my first sabbatical with this guy, Vivek Borkar, who's now at IIT Bombay, and my graduate student here, Aditya Devraj. The last time you had a crash course in stochastic approximation and some applications, just briefly mentioning reinforcement learning and empirical risk minimization. And we went through a lot of concepts really quickly. And the big thing was this stochastic differential equation and asymptotic covariance for stochastic approximation. And that's what I would call the hidden theory. I mean, again, anybody who works in stochastic approximation would laugh at me for calling that hidden theory, but I've talked to enough people in reinforcement learning to know that it's almost unknown in the reinforcement learning community, which is a real surprise. And that, I mean, I'm sure some people would take issue with that, but I mean, it's a very fractured community. Okay, so today, so basically, there'll be a bit of a recap, and then I'm going to explain what this ZAP algorithm is, and I'll have to walk through slowly. There's some real subtleties here. And then we're going to try to apply this to reinforcement learning, and that's going to require a crash course in stochastic control. So we're going to have to cover, dynamic programming equations in a few minutes. And then we'll go and put this to work. So what's really cool, though, is that at first sight, you'd think, well, that's obvious, but it'll never work. And the thing is that the fact that there's theory to support that this works is amazing, and how well it works blows my mind. I still thought it was I thought you were kidding when I first saw these experiments. Okay, so actually one thing, let's go back for a second. One thing I want to just mention again is that when you're doing Monte Carlo, so when you're just doing flat out Monte Carlo, you're trying to compute the mean of a random variable. We looked at this last time. The best thing you could do is this recursion and that rho equals 1. That's the standard thing you do for averaging a bunch of random variables that has optimal asymptotic variance. If you put a g over here that's not 1, you'll get higher variance. Okay? But then there's this ingenious trick of Rupert and Polyak where you actually crank up the gain. So by putting in a rho there which is less than 1, it's like blasting up the gain. It's like putting a gn on top that's blowing up. If you do that, you'll get an infinite variance algorithm on the top, but then you average the output of that and you get an optimal variance algorithm. And when you compare the standard Monte Carlo scheme with this double scheme, you see the central limit theorem looks almost the same. So it's optimal. Okay, so this is, though, these beautiful optimistic results. Really, it's very rare you see that for stochastic approximation. This is really special because you have a very special problem, just estimating the mean of a random variable. So although it's true under really general conditions, this trick has optimal asymptotic covariance. We'll show you results where it really sucks. I mean, just awful. And so there's, buyer beware. You can't expect this all the time. Okay. All right. So let's do it. So first, yeah.
What did we lose by averaging? We have to. I mean.
Oh, we don't lose a thing.
We don't lose anything.
No, that's the miracle of this. I mean, it's unbelievable that. So here it's all scalar. But we could have done this in the matrix case, and you could either put in a matrix gain, which I'll review in a second, or you can forget the matrix gain and just crank up a scalar gain and average the result. And in terms of asymptotic covariance, you don't lose a thing, which is amazing. It's absolutely amazing. But on the other hand, sometimes asymptotics are really sharp, like they are here. The CLT converges after 1,000 steps. It looks perfect. And sometimes asymptotics don't tell you much at all. That happens sometimes as well. I mean, an example is sometimes large deviations theory is a worthless tool for designing hypothesis testing rules because LDPs just take too long to kick in. Sometimes that's true, sometimes it's not. And I'll show you an example here where this asymptotic theory really doesn't tell you very much. Okay, so let's do it. So here's a recap. And this is just, so one way to optimize covariance is through a matrix gain. So we have this slightly modified Robinson-Monroe stochastic approximation scheme. They never had a matrix gain here. They just had a scalar gain. And you interpret this as a noisy Euler approximation to an ODE, assuming that Gn converges. And here, I'm always going to take the gain here to be 1 over n. And the GNs, again, is to optimize the asymptotic covariance and improve dynamics, which we didn't really talk about much last time. But basically, we're thinking about Newton-Raphson throughout this. And that's the main thing we really want to dig into in today's lecture, is what do we mean by this? Okay. Now, any computer scientists out there? Oh, yeah. I mean, you're hiding. So if you're in the sort of NIPS community, there's only one way you're allowed to analyze these algorithms. You have to have a finite n bound. So at time n, I have to tell you the probability of the error exceeding some epsilon. And I'd love that. I would love to be able to do that. And the thing is, though, forget it. All right? Forget it. It's just you're not going to get it, and it's not going to be informative. All right? Now this, I know it's asymptotic, and sometimes asymptotics don't tell you anything, but this is crisp, computable. This you can use for design. This just makes you feel warm and fuzzy. But it shouldn't make you feel warm and fuzzy, because the bounds you get will be so loose, they won't be informative. So they won't help you with design. They'll be so loose. And just, for the record, by the way, we had 1,200 views on YouTube, Aditya told me, as of this morning. So there'll be a big audience here. If you think you can do this for stochastic approximation, then I ask you to do this. Look at the probability that 1 over n Sn is greater than epsilon, where Sn is a sum all right, give me a bound. So I've got a finite state space Markov chain. I've got some function of that, and I have a sum, and I want a bound like this. That doesn't exist. All right. So if you can't just take standard Monte Carlo and get a finite n bound, then how can you expect to do it for some fancy stochastic approximation algorithm? All right. So this obsession with finite n bounds has got to stop. All right, CS people. If you can't crack, that problem is open. So there's one paper by Peter Glenn at Stanford, and there's a bound like that, but it's so loose it's absurd. It's worthless for any kind of anything. Yeah.
What is that? I epsilon?
Oh, that would be called a rate function in large deviation. So this function, what you ideally, so if I take a log and then divide by n and take a limit, I'll get something like epsilon, a constant times epsilon squared here. Basically, this is like linear in n and a quadratic in epsilon typically. So this again, if I take a log and divide by n, I'll get a computable limit, for Markov chains. But for finite n bounds, it's an open problem, completely open. Yeah. So, but this is a big fight. People see this in the CS community. They say, forget it. That's not, in the long run, we're all dead is a sort of, thing that people say. All right, but this is beautiful because we can compute it. We know the optimal gain in the case of choosing matrix gain is to take minus A inverse. And in that case, what you end up doing is it looks like you're just doing Monte Carlo averaging. That's some intuition. It sort of resembles Newton-Raphson. And it's super optimal. Again, it's the optimal covariance is given by this expression, and it's less than or equal to anything else you get with any other matrix gain. So it's, and that the proof of that is through like Kalman filter type arguments. You sort of make an association with just linear filtering. So you can do that. All right. So I think that this should not be ignored. That's the hidden theory. But then this. Do you see any resemblance? Let's go push back on me. This is nonsense, actually. I'll explain. So let's go back to this. So this is really the ODE when you do this matrix gain business that I was talking about. We have, x dot equals a gain times f bar of x. F bar of x was the averaged out function. But that a is something at the limit. Yeah. It's the derivative of f bar at the place you're going to eventually be. That's nothing like Newton-Raphson, right? Yeah. And so that's not what we want. And so that that's what we have to think about. So how could we get something closer to Newton-Raphson where instead of this being the derivative at theta star, have it the derivative of the theta I'm at right now? Okay. That's going to take some thinking. And that's one new idea from this work. And here's the idea. So we want an estimate of a at theta n, which is the derivative of f bar at theta n. And how do you do that? Well, here's how you do that. So you take your estimate here, just like you'd expect. So that's the gain. And you just do it exactly what you'd think for these guys. You sort of have a stochastic approximation recursion for these guys, where here this an is the current derivative. Right? That all looks natural, right? But there's a gain here, gamma n there, and there's an alpha n there. And you all tell me, what am I going to do? I want to forget the past. I don't want this uniform average of all these guys I've seen before. I only want to, look at recent thetas. I want to forget quickly.
2 time scale?
Yeah. And the 2 time scale in particular means that gamma n is going to be much bigger than alpha n. Basically that's how you forget the past. Just crank up the gain. And you put way more weight on recent observations and past observations. And what we're going to do is we're going to take, again, alpha n equals 1 over n. That's where we have this very crisp theory for the stochastic, for the asymptotic covariance. And in the experiments that we've looked at, we're taking this to be 1 over n to the rho, where rho is between 1/2 and 1. And that's it. All right? And that does it. So then you get the right ODE. Then if you actually go through and under Lipschitz conditions and nice conditions, you'll get exactly the ODE you want because this will just look at the recent nodes. So that's that. Right. So the zap is right there. That's what zap refers to, is a high gain. Really just to try to track the matrix. Now, of course, it's not necessarily stable. Why should this be stable? We're not, see, f bar is not the gradient of a convex function. We're not solving a optimization problem in reinforcement learning, which is the main motivation here. And Newton-Raphson, there's no reason it should be doing anything. This could be, who knows? And so this has been in the back of my mind all my life, that I've known what stochastic approximation's been about. Reinforcement learning's been about, but I never expected it to work in the context of reinforcement learning. So that's why it took a while to even do an experiment. All right. So general conditions for convergence are open, but we get really lucky in the context of Q learning. It's amazing. So that's what I want to explain in the next half hour. All right. And to do that, how many people here are fluent in dynamic programming equations? Oh no, this is going to be a short one. Okay. All right, so I said last time that all the functional equations in stochastic control of this form. I've got some mapping f that takes a function and a stochastic process. This is a real valued function, actually. And this conditional expectation is always 0. All right? And I said last time that this phi n is going to be state and action, and I'll make that precise now. I didn't make it precise last time. And then I said that all of these reinforcement learning algorithms, not all of them, but many, many of them, is what's called a Galerkin relaxation. So instead of searching over all functions H star, you search over a parameterized family. And instead of asking this conditional expectation to be 0, you take a adapted d-dimensional stochastic process, and you want the expectation of this product to be 0. So if this holds, then this holds for any d-dimensional adapted stochastic process eta. And now we're just choosing one. So the design of these algorithms, you've got to design the parameterized function class, and you've got to design the test functions. And so, yeah, and this is, in TD and Q learning, these are what's called eligibility vectors. You always see that. That's what this is. And what's amazing is that when TD learning was introduced, there was no motivation for the algorithm. And it wasn't until later on, control people got into it, that the interpretation as a Galerkin relaxation was made. So if you look at the original papers on TD learning, there wasn't really much motivation for the algorithms. Watkins came first. G-learning came first, where the motivation was really clear. You weren't trying to approximate at all. You were trying to exactly compute a value function. The form of the equations was copied in TD learning, and that was the only motivation. Okay. But again, these algorithms are special cases of stochastic approximation. I'm saying that to you, reviewers at NIPS and professors in New Jersey. Yes, you know who you are. Okay, so let's be more specific now. So that was very, very general. Let's be more specific. So let's take a finite state space, finite action space setting, just so that I can make statements that I know are true. Otherwise, you need special conditions. I've got a state process X and an input process U. These are also the actions. And I've got this probability of going to a set A in one hop, starting from a state X and an input U, and then prior history. It's a controlled Markov process because the prior history doesn't matter. So this conditional probability only depends on the current input or action, the current state, and the set A. All right. And if it's a finite state space, we'll take A to be a point. So it's the probability of transitioning from a state X to a state X prime. A will just be X prime. Okay. And we're going to have a cost function, which is a function on states and actions. And here we're going to look at discounted cost optimal control. Average cost could be treated, but it's a little trickier. All right. And there's a value function. All right. So we minimize this over all input sequences of the infinite discounted cost. And we have this initial condition. For each initial condition, we have this minimization. And it solves this Bellman equation. All right. So H star of X is the value function, and H star of X is just the minimum of something like that. I've got the current cost plus the cost to go. That's what that is. All right. So you see this in deterministic optimal control. It's exactly the same thing. The only thing different is you've got a conditional expectation there. So the infinite sum is, obviously if you look at this, when n equals 0, you get the C of X U. That's the first term. And you see that there. And all this is the remaining n equals 1 to infinity. So that's the derivation. Cool. You're happy. And you see there's a conditional expectation there, and that is consistent with a conditional expectation there. And we'll make that precise. All right. All right. So what did Watkins do in the 80s that was ingenious? We have this Bellman equation, which involves an expectation. And when you see an expectation, you think, I can use Monte Carlo methods to approximate the solution of that equation. Well, the problem with this fixed point equation is that minimum outside the expectation. You basically, for every U, you have to compute an expectation. That's like doing a whole bunch of simulations in parallel for each U. That's not a very nice thing to do. his genius was to take the thing in brackets and give that a name, call it a Q function. I don't think he ever explained why he called it a Q function. And why does he do that? Well, I'll explain. Well, first of all, 8 star is the minimum over U of Q star, right? That's what this is saying. And that means we can eliminate 8 star from this equation and get a fixed point equation in Q. You see an 8 star there, well, forget that. 8 star is a minimum of Q star. So eliminate 8 star from this equation, and you get another Bellman equation. So, so this I had a 8 star of xn plus 1. Now I've got a Q lower bar of xn plus 1. So because it's the same thing. Okay, so whenever you see a lower bar, I'm just taking the minimum over the second variable. And that's a fixed point equation in Q star. And now I've got an expectation of something, just something. And I can apply Monte Carlo methods. So that was Watkins' genius. It was this one beautiful idea that made everything work. And it turns out this is, if you know something about, optimal control, it looks just like the Hamiltonian. It's really almost exactly that. Especially when you look at this in continuous time, it's basically Hamiltonian, with the P of t plugged in. I forget it. Anyway, there's a paper on that I can share with you if you'd like. All right, so that's what you play with, and now we can go through and derive Q learning. All right. So, a few other things. So it turns out that we could have started the other way around. We could have defined Q star to be a value function just as before, where we fix the initial x and we fix the initial u. It turns out this sum is precisely the same as the Q function. So that's another way to think about it. So when this minimum, I'm minimizing over u1, u2, u3. I'm freezing the initial u. Okay, so one thing that's really useful in analysis, I'll remind you about this again later, is that there's a one-to-one mapping between Q functions and cost functions. So you give, again, in the finite state space action space, I don't have to worry about existence. Give me a cost function, this minimum exists, and it's a solution to that dp equation. Conversely, give me a Q, any Q, you can see that I can find the C just by taking this and subtracting that. So there's a one-to-one mapping between cost functions and Q functions. That's not true for value functions. And that one-to-one mapping, I'll call it this squiggly Q star. That's a key tool in analysis. So, in a second. Yeah. I promised you all this would be fun, and I feel like you're not having fun. I don't know. You just, all right. Okay, so now let's put this in the language that I used before. I said that every dynamic programming equation in stochastic control is of this form of the conditional expectation of something equals 0. All right? And you can see this is exactly like I had before. This is exactly some functional of Q star and some random process. And in this case, that random process is the state at time n plus 1, the previous state, and the previous action. And that's it. All right. Now here's the cool thing that's easy, I always forget to say. I can plug in any stupid, oblivious stochastic process U, and this equation will be satisfied. It doesn't have to be optimal, it doesn't have to be anything. Just plug in some stupid input. Now, what we're going to end up doing is we're going to assume that U is noisy enough, it explores enough. You'll see why in a moment. We're going to put in some stupid input. It has to be designed with some care, which I'll explain. Okay. So the Galerkin relaxation is, again, just to replace Q star with a parameterized family. So I've got a parameterized family, say theta is an RD, and I have to design some d-dimensional stochastic process if theta is an RD, and I want to solve this equation. And here it's really clear that I'll need to do something with the input in order to make this meaningful. And the typical thing you do is you have some sort of state feedback, but then you add some randomization to it. In the original algorithm of Watkins, you had to make sure that well, first of all, x and un turns out to be a Markov chain when you have randomized state feedback. The pair process, x and un, and you had to make sure you chose the randomized state feedback, so you visit every pair, state action pair, with probability 1 infinitely often. So you made sure that the bivariate process was irreducible. So for a big state and a big action space, that could take a lot of time to visit all those pairs. Okay, so these again are called eligibility vectors, and you've got to design this family, and that should be done with some intuition. All right. And this is still an open field. All right. So I can state this as a goal, and you can write down a stochastic approximation algorithm, but is it going to converge or not is pretty much open, except in certain contexts. Okay, Watkins' algorithm is this. So again, we're trying to solve this Galerkin fixed point equation, and here's Watkins' design. So first of all, it's a linearized parameterization. So I've got a big psi, vector, and you take zeta n to be exactly psi valued x and un. That's a really common thing to do. For your test functions, you just take that basis vector and use that for your test function. But here's the catch. Psi has an enormous dimension, because basically you enumerate every state action pair, call x and un the nth state action pair, and the nth entry of this vector is just the indicator function of that pair. So really, this is just a parameterization of all functions, all possible functions. So Watkins' algorithm is not an approximation scheme. It's a simulation-based method to compute exactly the Q function. That's something that you have to keep in mind. Now, in practice, what you do is you pretend your world is a Markovian with state space size 12, and you just apply Q-learning, even though the world is not like that. Even though the world is some very complex system, you pretend it's not. And what's beautiful is that Q-learning is so black box, you can just apply it, even though the world doesn't fit your assumptions. Whether it'll work or not, who knows. All right. Now, what's really fun, first of all, again, to my friends out there, therefore, Q-learning is a special case of stochastic approximation. But the thing is that you apply the theory and you'll find out that the asymptotic covariance is infinity if you just apply it, the standard algorithm. And basically, if beta is bigger than a half, the discount factor is bigger than a half, the asymptotic covariance is infinity. And really infinity. I mean, really, the rate of convergence isn't 1 over square root of n. Maybe it's 1 over n to the 0.03. It's so slow. And that's a big problem.
That last statement, is it obvious from this slide, or it comes from the one that you mentioned in the last lecture?
Yeah, it comes from when you write down the
I remember your covariance equation from the last slide, last lecture. So that
we need the eigenvalues of this A matrix to have real part less than minus a half. Okay. And the fact is that when you write down the A matrix, I think I have it in a bit, you'll find that beta comes in, and if beta is bigger than a half, then you can show the eigenvalues of that A matrix, or there's one eigenvalue that you can see is bigger than a half, and bigger than minus a half, and that messes things up. Yeah, I think I do have it in a moment. I think I have the formula. Okay. And so the question is, can we zap Q-learning? Can we apply this Newton-Raphson technique? And I assume no. I mean, this is an awful thing, right? I've got this. See, this is a function of theta. Forget the theta star. This is a vector-valued function. If zeta n is positive, as it is here, because of the min here, this is a concave function of theta. Is that useful? I don't know about Newton-Raphson for concave functions, vector-valued concave functions. I did some Googling. I didn't find anything. I mean, who knows if this would work? All right, but it turns out it does. So the answer is yes, we will zap Q-learning, and I'll explain to you why it works. All right. So first of all, we need help. So here is a really boring problem. I mean, can you imagine anything more boring? You've got a 6-state Markov chain, and the edges there refer to where you can hop in one step. And all I want to do is go to this place and go to bed. That's my goal. I want to go over there and lie down. So you take off the shelf Q-learning, and you run it. And here's just a histogram of one of the, I don't know, 20-some whatever parameters. You start at 0. So all the initial parameters was initialized at 0. And you've got this histogram. So this is like 1,000 independent simulations. And you've got this ball here, and it does converge. And we proved it last lecture. We know Q-learning converges because you can show the OD is stable. But it'll take 1 trillion steps to get to where it's supposed to go. This is after 1 million samples. It's below 100 when it's supposed to be at 486. It's amazing. And so people whining about Q-learning being slow for so long, they could have picked up any book in stochastic approximation and seen why. So in this example, the rate of convergence is like 1 over n. We haven't worked it out yet, but it would be 0.02 or something. 1 over n to the 0.02 instead of 1 over square root of n. And that's the reason for this problem. So we need to do something. All right, so let's go through and look what the A matrix is. So I will be able to answer your question and all of that. So the F bar of theta that we like to look at is of this form, and it's this big ugly mess here. And A of theta, remember, is the derivative of this at a particular value of theta. Now, for a linear parameterization, that's really simple. That's just going to be the basis vector. Now here you've got a minimum, and at least we're lucky there. We've got subgradients all over the place. And so we can forget about derivatives, but just look at subgradients. And at points of differentiability in particular, here's A theta. Okay. So you basically have your psi, your basis vector there, and you've got psi here, but then evaluated a particular u. It's the minimizer. So it's a policy associated with parameter theta. Okay? So this policy is the argmin of the Q function. Okay? But this is a policy you'd use if you thought theta was the best theta. So when you're all done, don't forget, you have to choose a control law. Your control law will be that. And once you decide the Q function that you think is good. Now, remember, for Watkins' algorithm, zeta n is the same as that. So you've got this minus, you've got negative and positive definite matrix. That's nice. And this times this is just some matrix with non-negative entries. What ends up happening is you can apply the Cohen-Frobenius theory to analyze the top eigenvalue of the inverse. And it turns out that, because this outer product is similar to this outer product, you can get a bounds. And for beta bigger than 1/2, you find that asymptotic covariance is infinity. Okay. And that's true for, there's 2 different ways you can implement off-the-shelf Q-learning. I mean, one is just the 1 over n, and one is where you keep a counter of how many times you visited a particular state action pair. And so you have a different gain for each theta value. Well, the same is true for that.
And here is where, the thing that you mentioned to me, or I asked you before the lecture, that the control law that you specify here should be in such a way that you need to visit each state action pair infinitely often.
Yeah, for Watkins' algorithm, that's right. Okay. Yeah, and so if you had a parameterized family, you'd have to choose a U so that this matrix is invertible. And so that'll require a bit of exploration, possibly. That's right. Yeah, in order for this matrix to be invertible, you need to visit every state action pair infinitely often. All right, so there it is. So then you just go through and blindly apply this. We've got our F is that thing that's in this red color, You just take that and plop it down. And then we have our matrix estimates. Well, we've got our that's what I called AN before, that whole monster. That's what's right there. And we go and apply it. Okay, so AN was this derivative, which I'm just writing down once more here. It's Newton-Raphson. It's the closest we can come to Newton-Raphson. And why should this work? There's no intuitive reason. At some point, we're going to have some beautiful explanation, but right now we don't. It's just calculus, and I wish I had an intuitive reason why it works. But I'll give you a proof right now. Why it's stable. Is it clear, the algorithm and all that? All right. Stable. All right, so here's this. Remember I said that there's a one-to-one mapping between cost functions. I want to talk about general cost functions. This is the only symbol left. There's a squiggly symbol. So that's like that's actually called var sigma in LaTeX. So that little squiggle, for any cost function, there's a Q function, and conversely for a Q function, I can find a cost function. It's a one-to-one mapping, and I didn't know it like that. And so basically, again, given a C, that's like a C, I can solve this equation to get a Q, and conversely, given a Q, this C is just that Q minus that sum. So there's a one-to-one mapping. Right? Now the reason that I'm emphasizing that is that to analyze this ZapQ learning, it turns out it's much better to look at cost space rather than Q space. Make it a change of variable. And the fact that it's a one-to-one mapping is gold. All right, and here it is. I said I'd give you a proof. I just realized I'm not giving you a proof. I'm just telling you the conclusion. It turns out that if you take the given Q function estimate at time t, so you go through and you construct this ODE, and then you look at it, and what you can show is that the Q of t goes along, and it's in some piecewise linear orbit. And at first sight, I was really scared there'd be some infinite limit cycle, like a piecewise linear infinite limit cycle, that it would never converge. And then it turned out that if you made a change of variable and said, forget qt, let's look at the, for each t, look at the corresponding cost function associated with. Okay? Turns out that solves this ODE. Can you imagine anything so lucky? I hope all of you are that lucky someday, is to take some hack algorithm and then play around with it and find out that it's that trivial. Who would have known? It's just, why is somebody calling me? It's amazing. So the ODE is stable, and the zeta t's converge to C, and therefore, qt converges to q star of C, which is q star. Absolutely awesome. And this is the ODE for Monte Carlo. If you're just doing boring averaging, the ODE becomes this. It looks like this locally. So if you start out near the optimal Q function, it has the same ODE. So you get Q dot equals minus Q plus Q star, but that's only locally true. If you start far away, you end up with this strange piecewise linear behavior, and that's because this Q star function is concave and convex and piecewise linear. And so this actually has a piecewise linear trajectory. Okay, now, and the proof, now I regret that I didn't include a proof. Basically, it's when you, forget it, no, it would take too long. But it's again, we're exploiting the fact that there's a minimum here, it comes up, and one ugly term drops out when you playing around. That's the magic. That's the thing I don't understand. So A of theta is the gradient, the derivative of f bar of theta. But it also turns out to have you have this representation. It's bizarre, and that's because of the minimum. It just comes out that way. It's really strange. You look at this and you think, well, we've got the product rule, so you'd have two terms. If you take the derivative of this, you think there'd be two terms. But one term drops out and you get this. So because of this strange formula for f bar of theta, you get this ODE. That's how it happens. And so that's just a bunch of algebra. So again, next year I'll come back and say that there's some Hamiltonian, and it turns out we're solving a variational problem, just like Michael Jordan tackled some recent work on accelerated gradient methods. So next year there'll be some beautiful theory. I don't know, something in, quantum computing analysis. But right now it's just algebra. Okay. All right. So let's just now go through some examples to illustrate what happens. So again, look at this boring example, and here's what happens. Try anything you want, and they all fail. Take speedy Q-learning, it's called. There's a polynomial Q-learning. There's Polyak Rupert averaging. What this is like the worst of the bunch and the best of the bunch, and then everything else is in between. That's basically what that is. So this is a Bellman error, so it's sort of a norm error in that Bellman equation. And this is after a million iterations. The Bellman error is still, it doesn't decrease much after a million steps. Well, if you use this sort of Newton-Raphson sort of method, it just computes it in comparison. And so it shows that you really do need that sort of Newton-Raphson part of the algorithm. The asymptotic theory is not enough. So even though Polyak Rupert averaging will give you asymptotic covariance, it's not doing that well. So again, it's true. You've got to be careful. The central limit theorem is amazing, but sometimes it's not that informative. Sometimes it is, sometimes it isn't, and you just don't know.
So every iteration here has an inverse term, right? Computing an inverse.
Yeah, there's a computational issue there. Yeah. There's an n squared complexity. Yeah.
So might not be fair to compare every one iteration here to one.
Yeah, that's absolutely right. I agree. I mean, in terms of computational complexity, we definitely need to. We know that we have an n squared complexity that we have to take into account.
Then that shifts.
And there's no way it's going to make up for that. But still, because I don't know when this is going to come down. Yeah. So in this case, no way that matters. But when we get to higher dimensions, we weren't looking at such a dumb problem. Well, let's come back to that at the end. But the fact the computational complexity issue opens up all sorts of areas for research. Okay, so here's the thing. So if you did, so Rupert proposed something that he called stochastic Newton-Raphson back in the 80s, and it was really just averaging all the ANs. Basically, I mean, it was a little bit different, but just averaging all the ANs. And when you do that, we don't get this beautiful ODE. We haven't yet even been able to prove stability. I don't know if it's stable, and it doesn't perform as well. It performs surprisingly well, but not nearly as well as when you have the 2-time scale algorithm. Right? Now the other thing you could do is say, well, it's not fair to use a gain of g equals 1 for Watkins, because we know that that's not a good idea. But we know that because we read the stochastic approximation books. Okay, so we can go through and try to find the scalar gain that optimizes Watkins and see what happens. And it kicks ass. Compared to these other methods. So it turns out you have to take g equals 1500 to get the optimal variance, and that shows how small those eigenvalues are. So this is for a discount factor 0.99, which is not that big. I mean, it really isn't. I mean, it's a horizon of 100 or something. That's not like a huge number. You see a lot of volatility, but it's awesome compared to these other methods. So the variance is huge, but it's good. All right. So all right. Okay. So the CLT is really nice. Okay. So this is after 10,000 steps. So this is entry 18 and entry 10. How do we choose those entries? This was the worst entry, where the CLT was the slowest to converge. and this was the best. So we did 1,000 independent runs, and you say, wow, the CLT is not working well at all. Bullshit, it's perfect. So red is theoretical CLT. I think that's like a perfect predictor of what we see. MATLAB might disagree and make these look different, but that is awesome how well it works after just 10,000 steps. And then if you go to 1,000,000, it's completely perfect, in terms of prediction. So the central limit theorem in this case, it's a really good predictor of performance. All right. And in terms of if you actually look at the local, again, if you look at the Bellman error, and you look at sort of local convergence, suppose we're really kind to these other algorithms, and we initialize them very close to where they're supposed to be, at theta star. So remember that the histogram I showed before, we initialized at 0, and Q-linear was just slowly crawling to theta star. Suppose we just said, here's where you want to be, let's start you there. Watkins still sucks, even though we started at the exact right place. So with a gain of 500, it's the Bellman error is way out here. The histogram is awful after a million samples. If you crank it up to 1,500, we see it's much better. And speedy in terms of the Bellman error, it's actually the Bellman error is not so bad. You see the histograms between 0 and 25 or so. But look here, the scale here is 160 for these competing algorithms, and here it's 50. Okay. So it's so if we really if we're fair to ourselves and stretch that out, then you could see how much dramatically better it is to use these linear Epson-like algorithms. The only reason we use this scale is we wanted to keep the green guy there, with a gain of 500. So Polyak-Rupert is like this uniform Bellman error of this huge range, and the single timescale algorithm doesn't do as well, but does pretty well. But when you use the two timescale algorithm, it's just very, very dependable. It's awesome. All right. And this is just another way of seeing this. So you can see the slope is right. We're getting the right slope for these three different schemes. Because I'm sure that the single timescale algorithm, I'm sure once we prove stability, we could prove it has optimal algebraic covariance. That's trivial, because once you get in a region, a certain region of theta star, it's just like Monte Carlo. It's trivial that it has the optimal variance, but the constants are very different. That's all. And these other guys just don't have optimal variance and given slope. All right, here's a fun one. So, completely changing gears now. Let's look at something complicated. Let's optimize our options strategy for trading stocks. All right. So this is based on a sequence of papers. The first one published with John Tsitsiklis. Ben Van Roy was a student back in the 80s. He's now a professor at Stanford. And they were looking at a particular optimal stopping time problem in finance. I'm not going to derive the formulas for you. It falls in the same categories I showed you before. There's a functional fixed point equation involving a conditional expectation. You look at a Galerkin relaxation, and you get a Q-learning algorithm. And you can apply the theory as here. So I'm not going to show you the equations, just the results. So the state space is R100. Basically what they're taking is the observation of prices now 1 step back, 2 steps back, up to 100 steps back, 99 steps back. They're just pretending that's a Markov process. And the Q function is 10-dimensional, and it's just gobbledygook. There wasn't a lot of motivation for the function that was chosen in this paper. Our motivation is not to make a killing on Wall Street. It's just we want to compare. What happens when you use this theory and apply it to a well-studied problem. And this is something with several papers studying this. So if you look at the A matrix, and you look at the real part of the A matrix, they're negative, but you've got a minus 10 to the minus 5 is the most negative, and then here you have a it's not that bad, but what is it? Actually, it's not as bad as I thought. It's there is the worst eigenvalue actually. Wait a second. Wait a second. Is it minus 0.1? No. I guess so. But actually, yeah, I didn't. Actually, it's not as bad as I thought. The worst eigenvalue is less than minus a half, but it's not that far off. It wouldn't be too hard to fix this.
No, minus 10 power minus 5.
Yeah.
You need 10 power 5 gain to.
Wait.
The
The
smallest
slowest one is on the top.
on the left,
Yeah.
the first.
Oh, I'm sorry. The first time I made this mistake ever, and that's on camera. I flipped this over around. Now we'd have to pull this down. Sorry. So this is practically 0. 10 to the minus 5, everybody, and it's funny. It's this minus signs that can be confusing. We'd have to multiply by 10 to the 5 to make the roughly on the order of 10 to the 5 to make those worst eigenvalues be less than minus a half as we wish. So, all right. So yeah, all of these have been, a real part of lambda is bigger than minus a half for every lambda. So they didn't analyze the asymptotic covariance, but they saw something was wrong, and in later papers they introduced a matrix gain. Right? And so I'm not going to give this to you, but basically they took the positive definite part of A, and they just used that as the gain. And then they also cranked up, or the negative definite part, the minus excitation of psi transpose. And then they multiplied that by a large constant, and then just by trial and error they found the best constant. So that was their GN. So GN, again, the excitation of psi transpose times the scalar, and the scalar was chosen by trial and error until it worked well, in their opinion. All right. And so here's what happened. So we came back years later and looked at, use Monte Carlo to estimate the A that comes up. Use Monte Carlo to estimate the G that comes up. So this took, weeks and weeks just to get a really accurate estimate. And then here are the eigenvalues. So they succeeded. Here's the miracle. Not applying the theory, but just through trial and error, when they got the best constants, they got their worst eigenvalue be minus 0.525. It's absolutely amazing. So he just made it to have a finite asymptotic covariance. So it's just purely by, the math was guiding them, but they didn't know it. It's amazing. All right. So that's that. And then you compare it. And they have a finite asymptotic covariance, so we can compute the theoretical variance. And here's what happens with ZapQ learning. You've got the theoretical and the observed, and you can see it's not quite as predictive. This is a really numerically unstable problem. That A matrix is barely invertible. It's so ill-conditioned. It's crazy. So the fact that the CLT works at all is amazing. So this is after 2 million samples. Entry 1, I guess, was the worst, and entry 7 was the best in terms of CLT solidarity. And here I don't think it's too bad. Here, that's a bit sad, the theoretical versus observed. But with this, the CLT falls apart, and you can imagine they're so close to having infinite CLT that probably the rate of convergence of CLT is very, very slow when you're that far from satisfying the assumption. Remember, their eigenvalue is minus 0.525. If it was minus 0.5, the asymptotic covariance would be infinity. And so there's probably a lot of numerical issues there. The CLT doesn't work. All right. And in terms of what you get, what you really care about is the average reward, a histogram of that. And forget about this. This is just, different time horizons. Let's go to the end. After 2 million samples, so ZapQ learning gives you the highest reward and always the same, basically. It gives you 1.23 every time. And the algorithm they proposed with G equals 200 was actually, quite good, but has, I guess you can't see it all, but it has a much bigger dispersion. Basically, it's way less reliable what you're going to get. I forgot which was their gain. Was it 100 or 200? Yeah. So you crank up the gain a bit more. That's what I recall. Yeah, I should know that. But with blue, you can see it's hiding there. It's sort of uniform almost. So sometimes you'll get a pretty good answer. Sometimes you won't get a good answer at all. If you see, I don't know if you can see it. There's little bits of blue all over the place here, and that's that. And this is quite an easy thing. So in terms of complexity, it's the same. So there's no cost there. They have a matrix gain algorithm, so do we. All right, so in terms of conclusions, let's go back to your point. This is after this beautiful walk to Point Reyes several weeks back. So the asymptotic covariance is a beautiful design tool. We saw that sometimes it's also predictive of performance. Like in the case of Watkins Q-learning, it's dead on perfect for predicting performance of the algorithm. In this case, this finite example, it's not as good, but it's pretty good. And this particular example with finance was numerically horrible. I mean, the matrix has a condition number of like 10 to the 4. So we're not going to do that in reality. We're going to create much better conditioned problems to begin with. So we'll choose a basis functions that are more better conditioned, all of that. The one example was the fact this 1500. I don't know any way you'd get that 1500 except through this technique of solving the Lyapunov equation and getting this thing, getting this value. All right? But a big thing to remember is that there's two things going on here. So DT and I are not saying asymptotic covariance. Two things are working here. There's the asymptotic covariance. I believe in that. It's really useful. But that Newton-Raphson business was important. We saw that with the comparison of Polyak averaging versus ZAP-Q learning. So we didn't have that Newton-Raphson part, and that's why we weren't taming the dynamics in a way. And so the bad dynamics of Q learning were maintained. And so when you keep those two things in mind, it gives you a whole tool case for algorithm design. So in terms of future work, conditions for a stable algorithm under general function approximation setting is an open problem at the moment. Now it turns out the OD analysis goes through. It's amazing. You still get something like C dot equals minus C, blah, blah, blah. It's not C anymore, it's something else. But the OD analysis goes through for any function approximation setting. We just don't know if A is invertible. We don't have general conditions under which A of theta is invertible. So that's the gap there. For optimal stopping times, it's been resolved over the last month. So that's solved, I think. There's some technical issues, but they're minor. Nothing that would bother anybody in this field. But then there's your point. What we'd like to do is just keep these things in mind. And what's cool is, for the matrix gain, you can just pick up a book. What's your favorite reduced complexity version of Newton-Raphson? And come up with a stochastic version of it. And then we can do things like optimize the variance by, say, a scalar gain, because we know how to do that. We can use the Lyapunov equations, find the optimal scalar gain for a given matrix gain. And most likely, in high dimensions, certainly that's what's going to happen. And I should say that right now, the fashion is to say that matrix gains are absurd. Mike Jordan, on Friday, said this could change at any moment at Boyd Fest last week. So I'm not saying it. It depends on the problem. In robotics, they never have high-dimensional problems. And it doesn't make any sense not to use a matrix gain. Of course, when you're looking at this AlphaGo, you're not going to be doing a matrix gain with a million variables. It depends. But that's going to be fun. I think it's really going to be fun to see, look at compromises, and that's it. So thank you. Yes.
Could you please explain more on how to choose a good Q-state function? How we know that's a good choice?
Yes. Well, the thing is that I can give references on this. So a lot of problems in control, you have a lot of insight into the structure of the value function. So in queuing models, like where you're looking at scheduling, routing, and you've got delay costs, we know the value function looks quadratic. It's like a piecewise quadratic function plus some junk. And you just plug that in. I actually have a survey paper on taking naive models, solve them, or approximately solve them, and then you take the solution of the naive problem, very, very approximate model, and you plug that in for a basis for the original problem. So that's one technique I know. I mean, a lot of problems we look at in control, you have convexity. I mean, we have growth rate, so it gives you all the structure you can use. So that's one thing. Often we have a lot of structure in the problem. And in finance, I mean, there are so many heuristics, and you just plug them in. And that's something I'm looking forward to doing. We know there's heuristics on stopping rules in finance. And I don't think that they've properly used that in basis design. But then there's a question of designing the Q function so that the minimum is easy to compute for control. So when you're all done, you have to have a policy. And so you're doing that. And also we want this algorithm to be nice in the sense of that A of theta, well, it's not there, but we got right there. That thing has to be invertible. So of course, I mean, hopefully you can design it so that's true as well. But that's something I don't know anything about. That's an open question. Yeah.
Would it make sense to add, so in the cases where A is not invertible, would it make sense to add a regularizer term in some sense?
I don't know how to do that yet. I mean, the thing is that if A were non-negative definite, then, for symmetric and all that, then we could add a little something to fix it. But here A is not symmetric, and we don't know if it has negative, we don't know anything about it at this point. So
there's no way to estimate sort of the values close to zero and then suitably apply.
Well, the thing is that as long as A has, what's got us stuck right now is that for the general function approximation setting, this A of theta might have a zero eigenvalue, and then we don't know what to do. And a colleague of ours in France came with a counterexample, where the eigenvalue really was zero for some special chosen example. So it really is an issue for general function approximation. Not for optimal stopping, just for completely generic function approximation.
And what does the eigenvalue 0 correspond to? What's that?
In that case, I don't think it was an intuition. Yeah, I don't know. No, I didn't see any intuition when I read it. It was just it's just some It's just the fact that there's a lack of compatibility. That minimum is the problem. Where's our A of theta? Wait, yeah, the fact that there's a minimum here makes this function and this vector very, very different, And that difference isn't so important for Watkins. It's not so important for optimal stopping, but in general it is. And so we'll have to figure that out. Yes.
But where the exploration part comes in?
Oh yeah, so in Watkins' algorithm, you have to make sure that the joint process XU is an irreducible Markov chain, meaning you visit each state action pair infinitely often. So that's where the exploration comes in there.
So that's the only, because I'm just wondering whether, because it seems like there should be a better randomization strategy that may lead to a better conversion.
Well, that's what's so cool here is you're putting in junk into the system, and what comes out is the optimal policy. Now, what some people like to do, one thing that there's a literature on, is to do an oblivious randomized policy with, say, probability 1 minus 1 over n. I mean 1 over n, and with the remaining probability, you choose what you think is the best policy, things like that.
Yeah.
And you could still prove convergence under certain conditions.
Yeah. So I'm just wondering, for different randomization policy, does that affect the analysis?
Oh yeah, because it'll affect your A of theta. That's right, absolutely. Yeah, that's right. So and that's the thing is, if you don't explore enough, your A of theta could be very ill conditioned. Yeah, so absolutely.
Maybe probably design can make L theta more well conditioned.
Yeah. So yep, absolutely. So if you have a bad input, you'll make A of theta horribly conditioned. Absolutely, and that's part of the picture. And that's why we should do an experiment, but I have a feeling that the results they won't be so pretty if we do that sort of optimistic Q learning, with probability, you only explore with probability 1 over n. Or something.
That's most people are currently doing, right?
I don't know if that's true. I don't know why they would be. I don't understand the motivation. I don't know why you wouldn't just learn first. You know, I don't know what the impatience is about.
To learn first, you need to like test each action like infinitely often and update that.
Well, we shouldn't be doing Watkins, but no matter what, you're going to have to be doing. You'll have to do even longer. I mean, the thing is, if you don't explore, you know, it'll take longer to learn. You're going to have your robot buzzing around for years, because you'll explore much less if you take what you think is the optimal action with high probability, and you explore probably 1 over n. So that billion steps will turn to a trillion. I think. I don't know. I don't think it's a savings of time. That's my gut. That's what my gut tells me, not math. Okay. Thank you for your attention.
Thank you.